So we have two presentations in this session, so each about 25 minutes with 5-minute break in between. So let's just jump in. So our first speaker is Hector Mera Couto. Couto? Did I say that right?
Sure.
Sure, okay.
Yeah.
And he's gonna tell us about harmonic oscillators and addictive behavior.
Yeah, thank you so much. I will start sharing my screen. I hope I don't share something like embarrassing. Well, this is the meeting room. Let me find it in here and let me go to the first page. I hope this will work, okay? It's a lot to unpack, but done. Thank you very much. So thank you so much for having me. It's really a great pleasure. The little I've been to the conference, I'm loving it. So my name is Hector Mera. I teach mathematics at Montgomery County Community College, and the title of my talk is Harmonic Oscillators and Addictive Behaviour. And it's nice because, when you think about addiction, typically you think about somebody going somewhere, getting something and going back somewhere and going back and forth, so it has this kind of oscillating quality to it. This is a kind of researchy-like project. So it's a kind of like exploratory research project that was born out of student projects that I have for the differential equations class that I teach at Montgomery County. So I will tell you about those a little bit. I will tell you about a very clever model by a guy called Sprott, Professor Sprott, which has this beautiful model of addiction that I will discuss. But I will tell you also about empirical facts about addiction, and that the model in its original form does not describe very well addiction. It does, but not entirely. So I will tell you about escalation, and I will tell you about de-escalation, how I include those phenomena into my modeling. I will tell you a few words of work in progress regarding that actually having fits for real experimental data using these models, and then a little summary. So in Math 223, I run various simultaneous projects, group projects with my students. So there is the dynamical models of love, which my students love very much. So I have 3 groups of students working there. Gliders, 1 group, delay equations, 1 group, and neurons, another group. So they left out dynamical models of happiness, which was the one I liked the most. So I started to look into it a little bit. So this guy called Sprott has this paper. And if you actually look him up, if you don't know about him, although this community probably you all know about him, he has a treasure trove of beautiful papers. It's crazy, It's crazy that there is somebody like Sprott. When I grow up, I want to be like Sprott, having all these beautiful papers. And in this one, he has a section that is talking about drug or other addiction. And if you look at the equation there, I don't know if you can see that zoom like lens. If you look at that, that is a harmonic oscillator equation on the left-hand side with critical damping. So it's a critically damped harmonic oscillator with a forcing term. The forcing term is a sum of delta functions. So these spikes that you see here are those delta functions. And they represent dosing, so intake of drug at certain times. And they are very, very narrow. The R is the solution of the differential equation. And this H is the happiness, which is the derivative of the solution. So R prime, that R prime will be the happiness. And what you can see is that you start at 0 happiness, and then you take the dose, and then the happiness goes up, and then it dissipates, and then it's time for the second dose, and then so on and so forth. And you can see cool things about this model. For instance, if you look at the first high, it's taller than the subsequent highs. So there is this kind of acclimation or tolerance built up into the model somehow. You also see that when you cease dosing, when you stop dosing the patient, so to speak, there is this negative happiness, that is withdrawal. So these things are into this model. So if you look at the model, you have that R prime, the derivative of the solution of this equation, is interpreted as happiness, that the forcing term on this differential equation is a sum of delta functions. So you can solve it by hand with your students using Laplace transforms. And you can see that dosing happens at regular intervals. So one dose when n is equal to 1, the next dose at n equals 2, 3, 4. So there is a unit of time between doses, and that is constant. And the effect of the drug is instantaneous. So if you look here, when we see the first dose, the increase in happiness happens immediately. So from one instant it's at 0, the next instant is at whatever arbitrary value you want to put it. So I hope that is clear. That's Sprott's model. So you can think about these forcing functions as being a sum of delta functions with, instead of n, Tn, and that Tn would be a different function of n, so that the dowsing is not at regular intervals. And of course, with my students, we reproduce the model results. So these are our own calculations. And you can see R prime, which is a kind of the solution, which is a kind of accumulated happiness. And you can see what happens is the following. When you start dosing, you start accumulating this fictitious chemical happiness, and then you have to give it back. When you stop dosing, it's gonna go back to its equilibrium state of zero happiness and zero accumulated happiness. So you accumulate all this happiness, and then at the end of it, you have to pay a price, which is withdrawal. So that is the kind of interpretation that the Sprott has of the drug addiction. And I want to tell you a little bit about what is known experimentally about addiction. So there is this comic called Rat Park by Stuart Macmillan, and it's telling you a little bit of the history of drug addiction studies. So in the 1950s and 60s, people actually look at rat experiments, which are quite cruel, by the way. So what they do is to surgically connect the rats to a self-injection apparatus. And then they put the rats into cells. And then they train them to press a lever. And that lever gives them a dose of whatever drug they are studying. And this is real data. So for instance, here, you have, pay attention at these triangles, which are the ones here, okay? These triangles are the pink and the red. So you start at low doses. So these are dosing frequencies, essentially. So how frequently they dose per day. So in day one, I don't know, 10 lever pressers or something. Day two, maybe 15, day three, 5, and so on. And then at day 6, they give them long access to the drug. So they have, they can stay there for hours pressing the lever. So what happens is that it escalates. So they start to press the lever more often on day 6, 25, on day 7, 90 or something. On day 13, 120. So there is this escalation of dosing, an increase in the dosing frequency. Then there is also this other paper from 99, but there are like a trillion papers showing this kind of plots. So I'm showing you 2, okay? Of that trillion, maybe you can find some of them that are more interesting. And again, you see the same thing. So this is the dosing frequency, the number of cocaine infusions per session as a function of the number of sessions, essentially, of time. So again, you can see that it starts low, and then as time progresses, they escalate their dosing. But at some point, they de-escalate. So if you look here, it's kind of at a constant rate of dosing. So the basic 2 facts that I will take into account in the modeling is escalation at the onset of addiction, this part where the dosing frequency is increasing, and then the de-escalation leading to a regular dosing. So if you look here, well, essentially, then maybe I can annotate. No, I cannot annotate. So if you look here at the beginning, that is when you smoke 1 cigarette a week. And then at the end, when you are 35 or 40, you are smoking 1 packet a day. So this is the constant frequency of packets of cigarettes that you're smoking per day. So Sprott's model that has regular intervals cannot account for escalation. It will never account for it. And the other thing is that even if you put here a different function of n, then it wouldn't account for escalation either. You have to determine Tn dynamically. Just a second. Let's see if I can do something. So just excuse me for a second. Yeah. No, it's okay. Leave it. Thank you. Anyway. So yeah, so essentially what happens is that yeah, I would like these TNs to be determined by the dynamics of the model. I don't want to put a function here, but I want somehow these equations to determine themselves when to dose. So that's what I try to do. So essentially, I want to remove this dosing at regular intervals from Sprott's model. So yes, so what I'm going to do is to make the Tns functions of R prime somehow. And I'm here using something called functional notation. So it's some kind of functional of the derivatives of the solution or the solution itself. I don't know, it's just a guess. But the way I implement the guess, so let me put it in here, is by keeping the equation with the forcing term with the differential equation, and the Tn is going to be determined by this threshold equation, which I call happiness threshold. So when R prime, the happiness, reaches a certain threshold, you need to take another dose. So let me show you. The boundary conditions, by the way, are these ones. Okay, 0 for R at 0, and R prime is also 0 at 0. So let me tell you how the threshold model works. So the threshold model is in red. So at the beginning, the first dose is given. So that is an input, the time of the first dose, which is essentially arbitrary. And then once you have the first dose, the happiness increases immediately, and then it starts to dissipate. And then the threshold here is at 0. So as it dissipates, it hits the threshold, then time for the second dose. Then it increases again, it dissipates, time for the third dose, when it hits the threshold. Then it increases again, dissipates, time for the fourth dose. Now, the picture in black, the lines in black, are Sprott's model with this kind of regular intervals. So in that model, you take the first dose at 1, then it increases the happiness, dissipates, second dose at 2, increases happiness, dissipates, third dose at 3, and you can see that you go a little bit unhappy because you kind of are waiting for 3 to come, and that's a bit too long, you are getting anxious. Then after 3, the other dose, and then you go very anxious until the fourth dose. So you can see that there is escalation, in fact, because if you look at the black dots here, those represent the dosing times for 4 doses in a Sprott's model. And the threshold model, those 4 red dots are the time it takes for you to get, the 4 doses. So essentially it's escalating. The time period between consecutive dosing is decreasing. So this is Sprott's model, and this is how the threshold model looks like. So now R prime, which is the happiness, it's going to be a succession of peaks, highs, and lows, but you are cutting the low short and then taking a next dose and so on and so forth. And when you put that into the model, it actually escalates. The doses become closely spaced. Now look at the following thing. If you have R, that's the cumulative happiness. You start at 0, and then you build up all this chemical happiness that you have to give back. But you are optimizing somehow the chemical happiness, and then you have to give a lot back. So if you compare the withdrawal for the threshold model, it's much deeper than the withdrawal for Sprott's model. In Sprott's model, the withdrawal is about 0.4, and then in the other one is about 2. So it's a factor 5 or something. So essentially, Sprott's model has some kind of tolerance built in because the highs get lower, and it has withdrawal on it. But the threshold model doesn't have tolerance. The highs stay at the same. So chasing the dragon kind of works. So if you accelerate your dosing, you can recover the initial height. And that's not a good thing about the threshold model. I think that in reality, people never quite recover. And in fact, there is tolerance, no matter how closely you dose. And there is withdrawal in both models, and the threshold model contains escalation. So it's more likely to mimic that escalating initial onset of a drug addiction. You can, because here I know the dosing times, and I know the number of doses, I can calculate the dosing rate. And in the Sprott's model, the dosing rate is constant. But in the threshold model, the dosing rate is actually escalating. It looks linear, by the way, but I don't think it's going to be linear. And you can see that this is not actually good, because you can see that at some point, it has to de-escalate. It has to stop you have to stop increasing the dose. You are not going to have a dose every nanosecond. At some point, you will have to go into a constant 1 packet a day type of thing. So this tail, this long time limit, seems more to me like the Sprott's model. And the short time limit seems to me like the threshold model. I expect reality then to be something like this, but I don't know. So just to enumerate, I think that the Sprott's model will be the long time limit of the actual dosing rate in an experiment. It models acclimation or tolerance. It models withdrawal, but it never ever escalates. The threshold model that I introduced here, it appears to be the short-term limit of the actual dosing rate. Models escalation, models withdrawal, but it never stops escalating. At some point in real life, it will stop escalating. And it does not model tolerance. So I needed to do some kind of different model because I want to model tolerance and I want to model escalation and withdrawal, and both short time limit and long time limit of the dosing rate. So there are two conditions. So one I have dealt with, which is this dosing at regular intervals, putting a condition, a threshold model that determines dynamically when the next dose is going to happen. The next thing I'm going to do is to get rid of this instantaneous effect. So what I'm going to do is to broaden the delta functions. So essentially in this forcing term, I'm going to replace the delta functions by top hat functions that integrate to 1. So they will have a parameter epsilon that you control how tall and narrow or how fat and short the top hat functions are. So those are the equations. Now I have the harmonic oscillator critically damped with the dosing. The dosing contains is determined the times for the dosing by the threshold model. So the happiness must be above or must hit a given threshold, must hit a threshold for the next dosing to happen. And then the first term is going to be like this, where the F functions are not delta functions, but these top hat functions. And this is what happens. So here you have R prime, which is the happiness as a function of time. Now, if you look closely, the dosing is not immediate. So it doesn't happen. It's just building up slowly, and then it decays and dissipates. So it kind of have this kind of like shape one way and shape the other way. And then the other thing that you can see is that the model seems to include tolerance on it. Essentially, eventually, that you need to take a dose just to be normal. And then you also have to pay a tolerance, a withdrawal at the end. But now it's much more reasonable. It's not going to be 5 times or something like that. And the same dynamics happens with R, which is the kind of accumulated chemical happiness that you have. So now it's not going to keep growing linearly, but actually to level off eventually. And then you don't have to pay so much in withdrawal at the end. If you make epsilon smaller, then it becomes more like the delta function model, because these functions here, in the sense of distributions, in the sense of a weak limit, they approach a delta function when epsilon goes to 0. So as I decrease epsilon, these things become more and more like delta functions. Sorry, like sharp spikes. Now I can look at the dosing rate as a function of time. And you can see that the threshold model is that always escalating model. Sprott's model is the constant dosing rate model. And now we have all these other models in between that escalate and then they level off, just like the experiment. So in the experiment, you have this initial escalation here, and then it kind of levels off. So fitting experimental data, because now it's very tempting to fit harmonic oscillators to rats in cages. Then you can calculate the frequency of the rat, things like this. So it would be interesting because it will tell you the natural frequency of happiness oscillations of the rat and stuff like that. So I'm in the last stages of of actually getting this thing done. But I have done it for mostly for the short time limit when you have escalation. But I didn't do it with the model itself. I used something that I call partial hypergeometric summation, and that uses hypergeometric functions to do it. But I can show you in my mathematical file here. I have some, what I do essentially is to get the data from the experiments, which are these things. And then there is some theorems that I use to define a fitting function, which is kind of this function here, which is closely related to the hypergeometric function. And that actually fits, in this case, is the cumulative dosing as a function of time. But as I said, it's work in progress. I have not really done it yet with the threshold model. So I only been looking at the short time phase. So just for the conclusions, it seems to me that harmonic oscillators can model addictive behaviors. But when you do it, you have to account both for escalation and de-escalation. Escalation, you do it by implementing this threshold model, where the dosing times are determined dynamically. And the de-escalation, you actually do it by broadening the delta functions. That provides a kind of like upper limit for the rate of dosing, because the top hat functions, they will not overlap. They will kind of like pile together. So having said that, I just have to thank you for your attention. I hope you enjoyed the talk. Thank you so much.
All right, we have some time for some questions. So are there any questions for our speaker?
I have one, if that's okay.
Sure.
I was just wondering if you could use this modeling to try to help plan how to use dosing to minimize the withdrawal if someone was trying to, say, break an addictive
Yeah,
behavior.
certainly it's a very interesting question and a natural idea that emerges when you look at these graphs. So it is clear to me, and there is some literature as well on it, that when you kind of go in this way, you are kind of minimizing the withdrawal symptom. Not with, you are not minimizing it because it's still larger than in the Sprott's model. But it seems to me that having some kind of regularity can help you optimize the dosing, yes, the withdrawal. In fact, maybe that's why we stop escalating, I don't know. But yes, very important question. Also having the parameters, and you can imagine a lot of things happening. You won't know until you play more. I need to play more with real data. So to get the real data, I go to the papers and I extract the data points from the papers, and then I fit those. But it's, the first thing I wanted to do was to account for the de-escalation phase, because very quickly when I fit the escalation phase, I realized that I couldn't fit the de-escalation phase. So that's why I developed these broad and delta functions to try to do that. But yes, important question. There is a clearly potential for some kind of advanced applications in pharmacology. Say.
Another question is changing the interval in Sprott's model at all related to the parameter in the harmonic oscillator? Like, do you get different behaviors if the interval is short or long compared to the frequency of that?
Yeah. So in this model, as it is in the Sprott's model, it is done using omega-0, the natural frequency equals to 1, and you have always the critical damping. So essentially, yes, the critical damping will introduce a time scale, and the spacing will introduce another time scale. So depending on how you space, so if you, for instance, go here, let me put the Sprott's model somewhere. Here. Imagine that you set a new dose, say here at the end, after the withdrawal, you start again, and then you make them. So you can have the withdrawal of the first dose. Yes, so you have, you have time scales. And in this model as it is, because it's critically damped, you have one time scale, which is related to the damping, to the damping time of the harmonic oscillator. And you have another time scale that is the dosing. So if you close you make your dosing rate large enough, so the time between doses is short enough, you can kind of build up, you will build up a little bit faster. So there is, but everything looks pretty reasonable. So there is no clear, it doesn't look like dramatically behavior. It looks like either you stop before it decays or you stop until it decays and dose. So it's pretty easy to grasp, I think.
Yeah, before you showed the results of the threshold model, I was wondering if there would be a way to adjust the dosing to get the two graphs to be the same. But I guess not, because your dosing intervals are decreasing with the threshold model.
Yes, certainly. That is the main thing. And in fact, if you just decrease the dosing intervals, it's kind of, in a way, it's not, because there is some literature on modeling using Sprott model, but they are putting the dosing intervals by hand. So essentially they are having the rats and they are recording those times and they are putting those in. And that is fair enough. But I think that it's nicer when the dosing rates are dynamically determined, because that's what happens in your brain. In your brain, it's like you start to long for the next cigarette. And at some point you are too unhappy not to have it. So that's how the threshold model came into life.
All right, thank you. So I think we're out of time right now. We have to get set up for our next speaker, but thank you to our speaker. Let's thank our speaker again.